Welcome to the Explainer. Today we're taking a dense, tangled Haskell codebase and totally transforming it. We're swapping out brittle, clunky conditional logic for a super elegant, highly performant architecture. If you've ever stared at a massive block of code and just thought, man, how do I make this cleaner and faster? Well, you are in the exact right place. We're diving into some real-world Haskell notes from a developer named Ang, who documented this amazing journey of refactoring document rendering logic for Pandoc.
So let's dive right into this incredibly relatable coding problem that plagues, honestly, so many of us developers. Drowning in complex conditional branches. You definitely know the feeling. You open up a file and bam, you're immediately hit with a giant wall of if this, then that, else if, and just endless guard clauses. It's not just an eyesore, right? It's a total maintenance nightmare. It leads to scattered logic and these redundant, processor-heavy computations. Well, today, we're going to fix that.
Here's our roadmap for today's explainer. 1. The branching problem. 2. The strategy pattern solution. 3. Implementing the new styles. And 4. The benefits of polymorphic dispatch. All right, let's kick things off with section 1, the branching problem. So we start by looking at this wildly bloated monolithic function called block-to-pandoc. In the original codebase, this single massive local function was basically trying to take on the whole world. It was responsible for rendering document elements, specifically things like headers and paragraphs, based on various ebook output formats like TXT, PDF, and EPUB. And to pull this off, it relied heavily on massive if statements, else clauses, and endless guard branches. It was literally trying to do everything all at once.
And this setup brilliantly illustrates exactly why that monolithic approach is just so bad. The logic for outputting the document is completely fragmented. It's just scattered across all these multiple pattern matches. Worse, you've got this tight coupling to specific, almost hidden variables like vol pad width and chap pad width. If you just glance at the function header, it is incredibly difficult to figure out where these variables even came from. And, as we're about to see, all this complexity creates a massive execution overhead.
Okay, so here is the absolute crucial point, the performance bottleneck. Imagine a document with thousands of blocks, paragraphs, headers, the whole shebang. In this old system, the program redundantly evaluates a boolean check against the format parameter for every single block. It's constantly asking, wait, is this a text file? Is this a text file? Literally thousands of times, even though the format of the document never actually changes in the middle of processing, right? Talk about a massive waste of computational resources, right?
Which brings us to section 2, the strategy pattern solution.
Here is our 3-step roadmap to rescue this code and move from a fragile, hard-coded mess to a beautifully flexible system. Step 1. Define a strict contract, which we'll call our interface. Step 2. Implement the specific behaviors for each ebook format. And Step 3. Glue it all together so it executes seamlessly.
Before we actually look at the new code, let's just anchor ourselves with the quick definition of dictionary-based polymorphism. This is the core mechanism we're using to replace all that hard-coded branching. So in Haskell, you can use first-class functions to create a record. Think of it like a dictionary that holds functions. You pass this record around, and it completely dictates how the program should behave at runtime, without needing a single if statement. Pretty cool, right?
So, step 1 is creating that exact record. We define a simple interface called render style. This is our strict contract. It contains high-order functions specifically for our document blocks, one called render header and another called render paragraph. Now, any format we want to support simply has to fulfill this contract. No exceptions.
All right, moving right along to section 3, implementing the new styles.
Now we create 3 distinct engines to actually handle our formats. First up, the TXT engine. This one is responsible for padding and indentation, and it relies on those previously hidden dependencies we mentioned, vol pad width and chap pad width. Next, we have the typeset engine for PDF and types formats, which handles page breaks and index markup, relying on a keywords dependency. And finally, a plain engine for EPUBs, which is really just a stripped-down default behavior with absolutely no extra dependencies. The beauty here is that each module is perfectly isolated with its own distinct responsibilities.
There's a great quote from the author's notes that hits the nail on the head regarding the philosophy here. Each strategy explicitly declares only the dependencies it needs to do its job. By isolating these modules, we are strictly adhering to the single responsibility principle. The text engine only cares about padding widths. The typeset engine only cares about keywords. Nothing is tangled together anymore. The dependencies are totally explicit and perfectly contained.
And finally, step 3, we glue it all together. We create this renderBlock function that uses polymorphic dispatch through pattern matching. So when renderBlock is called, it takes that render style record and the block of text, and it dynamically executes the correct style, whether that happens to be a header or a paragraph, based entirely on the runtime type. It's practically magic.
When you compare the two approaches, the difference is just night and day. In the old code base, the caller code suffered from serious tight coupling, manually checking case format of text, then PDF, then EPUB. It was just incredibly fragile. But with the new code, it simply calls render block style block. The caller is now completely decoupled from specific format implementations. It doesn't need to know how to render a text file or a PDF. It just trusts the polymorphic dispatch to handle the whole shebang.
Let's wrap things up with Section 4, the benefits of polymorphic dispatch.
By swapping out those brittle guards for polymorphic dispatch, we basically gained a superpower for our codebase. First, we achieved super low coupling because the caller only knows the abstract interface. Second, we gained incredibly easy extensibility. Like, if you want to add a brand new ebook format tomorrow, you just create a new strategy without touching the core logic at all. Third, we massively improved performance because the format strategy is selected exactly once on startup, totally eliminating those thousands of redundant checks. And lastly, the whole code base is just so much easier to test because you can isolate and test individual strategies entirely on their own. I want to leave you with this somewhat provocative thought about how you structure your own projects. Is your code base hiding a massive branching monolith somewhere that's just secretly slowing down your execution and making maintenance a total nightmare? I really hope this explainer inspires your next big refactoring journey and empowers you to swap out those clunky guards for elegant polymorphic solutions. Keep learning, keep refactoring, and we will catch you on the next explainer.